まり魂トゥビルダダドゥダダ固まり魂トゥビルダダドゥダダ君の顔見つめるほど I love you ゆるく晴れ渡る空魅惑のそのほっぺつねりたい Close to you so 風の中雲にふわり寝転んで観察ブランコの揺れる音あくびする坂道そうフィーリング旅に出よう手をつなごう空の匂いはいろんな色模様アクロスザスカイ渡る虹は君への愛いつまで君とやたら切ない朝曇り窓にシンゴビュー君の姿かたどる懐かしい足音が太陽くすぐるよマーサンシャイン笑おうたまにゆらりたまに水たまり流れる風の匂い背伸びする校舎そうにもビュー夢のほとり固めたり風の気持ちはいろんな色模様遊ぼうかい空の道は迷うことないどこまでも終わらない世界君と走り出す昔出会った道忘れてた蘇る遠い記憶が口笛吹いて通り過ぎる旅に出よう手をつなごう空の
everybody. Welcome back to Chem 121. We're going to finish up Chapter 6 hopefully today, or at least get most of the way through it. Maya's here. Maya, say hi. Maya. Maya. She says, whatever that means. Okay, now go away. I've put her back on the couch like 5 times. She's probably going to walk. Oh, she's actually going to go away. Okay, good. What do we got on the agenda? We have quiz number 5. That's due tonight. There is a 24-hour grace period after all quizzes that extends through tomorrow. So tomorrow's the latest. It'll close then, and you'll need to finish at that point, but probably just best to get it out of the way. We're also going to talk about lab number 3 very briefly, because there really isn't that much that I need to say about lab number 3. So let me see if I can... Yeah, that's what I want. So, on Canvas, if you go into lab worksheet number 3, on the modules tab, you'll find this document. Lab number 3 is basically a review of chapters 4 and 5. Normally what we would do is we would give you a modeling kit so that you could actually build these molecules. Unfortunately, we don't really have the ability to do that without you buying a model kit of your own. So the document goes through a lot of the material that we talked about, so including geometry and polarity and stuff like that, and then nomenclature, which we did at the end of Chapter 4 and then also at the end of Chapter 5 to name different things. So up here was the nomenclature for ionic compounds, and then we have covalent compounds down here. Basically, what this is going to amount to, I should say, is that when you get to the end of the worksheet, you're going to be given 10 molecules. And what you're going to have to do is you're going to have to tell me what all of these things are about them. So you're going to have to tell me the number of electron groups around the central atom, the Vesper geometry of the molecule, how many non-bonding pairs, what its molecular geometry is, and whether it is polar or not. So I have put in parentheses what I expect you to do for that. For example, if you count the number of electron groups to be trigonal planar, I'm going to draw a big X through that, because that's not what I'm expecting. I'm expecting a number. Excuse me. So, for instance, sorry, my tab fell asleep here. Here's what that will look like in a table. Let me get this out of the out-of-bounds area here. And so what you're going to do is, so let's say that the first molecule, for instance, and I'll just draw it over here. Oops, I can't click on that. Let's say that it was like, I should actually look at these to make sure I'm not picking one that you're doing. Yeah, so let's suppose that it was CO2, for instance. So CO2 looks like, I don't know how to get this on here without, I guess, hold on. Let me just do this. I'm just drawing CO2 really quickly in Photoshop. So if I do this, then maybe it will work if I click over here. Yeah, there we go. Okay, so now we can at least see it. Okay, so what I want you to do, you don't have to paste any pictures in here. This is just for the example. What I want you to do is I want you to enter the number of electron groups around the central atom. So that'd be 1 for this double bond and 1 for this other double bond. So for example, for CO2, I would type a 2 here. And then tell me what its Vesper geometry is. Well, anything with 2 electron groups would be linear, for example. How many non-bonding electron pairs are around the central atom? So I've indicated in this diagram which atom the central atom is with a blue arrow here. That would be 0. Don't accidentally count electron groups on the sides here. So these electron groups on this over here are around these oxygens, but this is not the central atom. We only care about the central atom. If you give me all the total number of electron groups, you're going to get the wrong answer. And then you just fill out the row like this, for instance, okay? So I want you to have something like that in your table where I have put numbers in the columns that expect numbers, and I have put words in the columns that expect words, okay? Because if you give me a worksheet that doesn't have any numbers in it, or it's all words or whatever, you basically get 0 points for this entire part, and that's no good, okay? So don't... Be careful that you don't make that mistake. I know in the past several students have done that. Down here, you're going to just type in names. For what it's worth, I'm treating this as if it were Canvas. If I detect a mistake in terms of spelling or of any nature, really, I have to mark it wrong, okay? So be very careful. These are each worth 1 point each, and it's all or nothing. So be extremely careful, and I would very strongly recommend against looking these up online, in case something online is following some other nomenclature scheme or something. Like if you're typing in a formula and you're going to like some chemical supplier and then copying the name down there and you copy the wrong name, I will just give you 0 for it. Okay, so follow the nomenclature rules that we have described in the class that are in your textbook, and you will do just fine. Okay, just be very careful you don't make a spelling mistake that leads you to some place where I can't realize what it is. That's really the only issue. You can make typos. So like if you misspell something like with an OU or UO or whatever, like you switch 2 letters, like I'm not going to mark that wrong. But if you land on a chemical that, or a name that describes another chemical compound, I do have to mark the points off for that. Okay. So that's lab number 3. That's due next week, and there's really not much else I have to talk about it because it's basically another worksheet like you did for the first lab, except instead of doing math this time, you're going to be naming stuff. Let me do this so that this isn't in the way anymore on my... There we go. Okay. All right. So going back to the content we were talking about yesterday for the lecture, we finished on this previous slide here where I had you calculate the number of moles of each type of atom in a sample. And so we were able to do that fairly easily, where we just took the numbers that were in the coefficient. So these numbers here... Oops, my pen isn't actually on pen mode. There we go. So these numbers here... Why isn't this working? There we go. That played a very important part. So we said that 1 mole of this big molecule would equal, for example, 4 moles of oxygen, or it would equal 10 moles of hydrogen. Something I realized I didn't mention until somebody brought it up in the Discord. These numbers that are being used, these are all exact. And the reason that that is the case is because they're counted. So you can count how many atoms are in a molecule, and that number is known. So for instance, in one molecule, there are exactly 10 hydrogens. There's not 9.9 or 10.1 or anything like that. So when you're dealing with sig figs, those numbers won't affect your result. But we were able to do that. And then earlier on in the chapter, oops, sorry, wrong key. Earlier on in the chapter, we were doing calculations. Oh, my pen is screwing up. Along the lines of this, where we could convert grams into moles, or even number of atoms or molecules or whatever into moles. So we have done all of the major calculations in this section. Now what we just need to do is put all this information together so that we can tackle any problem that's given to us. So this on the screen is a summary of what we did at the start of the lecture when we were talking about conversions between moles and something else, be that number of atoms or grams. Now, you'll notice right here I've written the word particles. This is my catch-all, so this could be for atoms or molecules or formula units. But importantly, regardless of whatever it is that I am describing here, it is the number of individual things. So because we're working with molecules, that's going to be a ginormous number. So you're going to see a bunch of these charts in a second, and I'm going to use the word particles, and particles is just my catch-all for whatever individual discrete things I am talking about, because I don't want to keep amending the chart. Moles, you know what moles are, and you know what grams are. Grams are just a mass, so those don't need further explanation. Now, also remember that you can go between particles and moles with Avogadro's number. Here's Avogadro's number. In case you forgot, said nobody ever. Nobody forgets Avogadro's number. You probably remember it already. It's just that unique. It's that catchy. And then finally, we learned how to turn grams into moles by using the molar mass. And the molar mass is the number that we get off of the periodic table. And then to summarize with what we ended the lecture with, we learned that using your formula, the numbers in the formula, you can convert moles of something large. So this would be, for example, the molecule. And this would be some part of that molecule. And we can interchange between those two by using formula subscripts. Now, what we're going to actually do with this is we can say, well, if I know how to turn grams into moles and moles into particles, and then I can do the same thing over here. Then, in theory, I can put all of those things together into a giant table that looks like this, and do any calculation I want to. For instance, in the previous section, we were doing calculations to convert moles of something into moles of its constituent parts. But instead, I could give you grams of that something, which you would then turn into moles. And then you could figure out how many moles of some component part there are in there. And then you could turn that number of moles into whatever you wanted to, either grams or particles. So having this little chart to show you where you are going in a calculation and where you are coming from is extremely handy for starting out. Because a problem might ask you, hey, here's how many grams of medicine you have. How many of the atoms in the medicine are carbon? And if you look at that and you have no idea where to start, then you run into a problem very quickly. And this chart can help organize your thoughts. And you could say, okay, I have a number of grams of medicine, so I must be starting with grams, and I must be ending with grams, because that's what the other thing is asking. How do I do this calculation? Well, I turn whatever the first thing is into moles, figure out the parts of that are moles, and then turn that into grams. And so you can establish a blueprint. And if what I described on the chart here sounds even remotely like, okay, I sort of understand what's going on, then you're going to be okay. You're going to be in good shape. So that chart's going to be on the screen for all of these example problems. We're going to go through a few of these together, and then I'm going to have you try some on your own. But the gist here is that we're going to be doing calculations where we start with something and then convert for each time we take a step on this chart. Kind of like how I've been writing out my conversions in blue or whatever over what I've been doing. This chart is going to simulate that. And then I'll just show it to you in blue on my screen as well. So you can see how the chart is functioning. Okay. Now, even though there is a chart that shows a conversion between one side and the other, you may not always need to do that. This is why I have these terms here, A and B. In a given problem, you're going to have to look at what the problem is asking you and how many substances it is asking you to work with and or identify. For instance, in a problem, I might ask you, if I give you 10 grams of CO2, how many grams of that are oxygen? And so you would say, okay, the things that I identified in that problem were CO2 and oxygen. And what you're going to have to do is say, okay, well, in this case, the first thing was CO2, and the second thing was oxygen. And then you'd replace all these labels as appropriate. So when I say moles A and moles B, what I mean are moles of some substance I introduced to you in the problem, and then moles of the other thing the problem is asking you about. If the problem only has one substance, for example, I ask you to turn grams of CO2 into particles of CO2, then there is no B substance, and you would just do something like this. I do that conversion. And so that's going to be actually the first problem that we do, to just show you that, like, hey, here's how we've been doing these problems. You could still use the chart. This is why I introduced to you those three relationships on Monday, where we had grams to moles, particles to moles, and then grams to particles. And then I said, we're not really going to use grams to particles, because that'd be something like this. We're not going to really need that, because this chart doesn't have a connector in that direction. So I'm going to encourage that you just get used to converting everything into moles all the time, because that will help us to just get into the mindset and the muscle memory, I guess you could call it, of doing these calculations. So let's look at a sample problem of this nature. So a sample of vitamin C, and here's the formula for vitamin C, weighs 0.250 grams. How many vitamin C molecules are there in the sample? So the first thing that we need to do is identify what are the substances in this problem that we're going to work with. So we've obviously got vitamin C. And so that's this. Keeping in mind that that formula is vitamin C, so don't include it as some other substance. And that is the only substance mentioned in the problem. So for our purposes, when we're doing these calculations, A is going to be equal to vitamin C. And then B is nothing. There is no B in this problem. So really, I've just introduced the chart, and we're not even using half of it. We're not even going to use the chart for this problem, really, because you could do this with what you already know from earlier on. And that's okay. The next thing that we want to determine is where on the chart are you starting, and what is your objective here? So what is the problem asking you? Well, it's saying, I gave you a sample that weighs this many grams, so we're going to start here in our calculation. I've given you a mass, and I want you to tell me how many molecules there are. So our objective is to get to here. And so each time I do a conversion to get from our start to our goal, each step is going to be a conversion that we write down. So I should be writing down 2 conversions as I go in this direction. So let's try the problem and see how that works out. All right, I'm going to put that just at the top so you can see it. And then once I've written down the numbers, we'll put the problem back up. All right, where is my... There's my cursor. Okay. All right. I'm going to just write down vitamin C. However, I do need the formula, which I'm going to scroll off the screen in just a second. So let me write this down, what this is. C6H8O6. And then what we're going to do, and I'm going to put this on the screen here. We'll just scroll this down a bit. Then what I'm going to do is I'm going to take my chart and I'm going to follow the blueprint. So I'm going to turn mass of vitamin C into moles of vitamin C. And then I'm going to turn moles of vitamin C into particles of vitamin C. We're just following the little chart that we've got here. So that's my conversion blueprint. And then you would just do the calculation like we did yesterday for each functional part, right? So I don't want mass anymore, so I'm going to do this on the bottom so it cancels. We'll turn it into moles of vitamin C. And then we can look at the conversion. How many grams are there in a mole of vitamin C? Well, 1 mole would be whatever the molar mass of this thing is. How do we get that molar mass? So you go to the periodic table, and you look up all the elements and sum all of their masses together, right? Or, alternatively, you go to Lentech. Well, I have Lentech on the screen here. Oops, hold on. So there's Lentech right there. So I've typed in C6H8O6, and it weighs 176.12. So we're going to clear that off the screen, and we're going to write that down. That's how many grams are in 1 mole. Then we'll do the next step. I don't want moles, so we'll put this down here to get rid of it. I'm going to turn that into particles. Well, specifically, what types of particles am I looking at? I'm looking at molecules. So I'll just write that down to be clear. In theory, you could just write particles everywhere, but it's more clear to write down what type of molecule you are looking for, or atom, or what have you. And then for this relationship, how many molecules are in a mole? Well, how many of anything is in a mole? Avogadro's number. And then once we've done this, these are the units that are left over, so those will be the units of our answer. And it's up to us to punch it in the calculator. And if you don't have a calculator handy, you can use Lentech, or not Lentech, I'm sorry, Wolfram Alpha, which I... So let me put it in the chat here, since the chat's pretty barren. There's the Lentech again, if you need it. And then I want the home page for Wolfram Alpha, not this calculation we did yesterday. So there's Wolfram Alpha. And let me get that on the screen so that we can see it. So there's our Wolfram Alpha here. And so I'm going to type in our calculation that we just did down below. So that would be, I always do parentheses around whatever's on the top. 0.250 times 1 times 6.022 times 10 to the 23, parentheses divided by... There's only one thing on the bottom, so I won't do that. I'll just put the number. But if you have multiple things on the bottom, make sure that you put these parentheses around it, in case you have to go like times whatever. So this is fine. And so what number does it suggest our answer is? It says 8.548 in a bazillion numbers times 10 to the 20. So how many sig figs should we have? We should have 3. So let me write that down. 8.58 times 10 to the 20. We can now clear this off the screen. And that should be our answer. So now last thing we'll do is sig figs. This has 3 sig figs. This is 5 sig figs. This is 4 sig figs, so our answer should have 3 sig figs. All right, lots of moving parts in these types of problems. And we'll just go put the answer on the screen there. All right, I got 8.55. Did I just read it wrong off of the screen? I did, actually. I skipped a number. It's 8.55. It was 8.548, and I dropped a number. That can happen. Be careful. All right. So that was a calculation that we did yesterday, more or less. So now what we're going to do is we're going to try a new calculation that is also what we did yesterday, but puts all of the pieces together, and we end up using the entire chart. All right. So this next example asks us about a sample of caffeine that has a mass of 0.10 grams. How many grams of nitrogen are present in this sample? So again, let's go over our strategy here. First, we got to find the different substances, if there are more than one. So the first one is caffeine. And then, is there another substance that we have that is not caffeine but is something different? And the answer is yeah, it's nitrogen. So what I'm going to do is I'm going to identify what my things are. So A will be caffeine, and B is going to be nitrogen. I'm also told that I am given a sample of caffeine, so I'm going to be given a mass, which means I'm going to start here. And I need to determine the mass of nitrogen that is present, so I'm going to move up to that point. So that means I need to turn grams into moles, moles of something into moles of something else, and then that turns into grams. That's the calculation that I am going to be doing to solve this problem. So let's go ahead and do that. And I'm going to write this out like that. So I need to know the mass of caffeine. I don't actually remember what the mass of caffeine, or the molar mass is. C8H10N4O2. I'm going to try and remember that. So that's C8H10N4O2. In fact, let's just zoom this in a bit. Maybe not. There we go. Now, according to our chart here, we're going to turn that into moles of caffeine, which we're then going to turn into moles of nitrogen, which will then turn into a mass of nitrogen. So I'm following the chart. Grams A, moles B, grams B. Now I just have to do the calculations. And set up my units such that they cancel out. Okay, how many grams are in a mole of caffeine? So in 1 mole of caffeine, how many grams are there? We'll go to Lentech to figure that out. So I'll just type in its formula, C8H10N4O2. And you can do this along with me just to make sure that you get the right number. But that's what I got, 194.19. Next, I need to go to moles of nitrogen, so I got to cancel out the previous unit, which is what I'll do there, to turn that into moles of nitrogen. And then we'll ask ourselves, how many moles of nitrogen are in a caffeine? How do we get that information? We go to the formula, right? And so that'd be this number right here. Per mole of caffeine, how many moles of nitrogen are there? 4. Because every caffeine splits into 4 nitrogens, right? There's a bunch of other things. We just don't care about them for this problem. And then finally, I need to figure out how many grams that number of moles of nitrogen is. Well, how do I figure out the mass of nitrogen? You could go to Lentech and just type in N and hit enter. Or you could pick up your periodic table or use p-table. In either case, in 1 mole of nitrogen, you're going to get something like this. And that's off the periodic table. That is the molar mass of nitrogen in grams per mole. I wrote the wrong thing. Ignore that. There we go. So now that we have done this calculation and have everything set up, we can just punch in all the numbers into a calculator or Wolfram Alpha or whatever. And so I'm going to do that. I'm going to just do that behind the scenes here because you don't need to see me typing in numbers every time. I think everybody knows how to use their calculator. So what I got was 0.029. Now, that checks out because if I'm looking for a mass of some part of the molecule, it's got to be less than the total molecule, right? So we can do a little like mental check here. This number is the whole sample, and this is just part of it. And so it makes sure, you should make sure, I should say, that when you do your calculation that the number that you're getting makes sense. For example, if I ask you for the mass of something and you get 7 times 10 to the 24 as the mass, that's very, very, very large. Something weighing times 10 to the 24 grams would be like the size of Earth. So if I'm asking you about a vitamin C tablet or something, and you tell me its mass, it should not be that big. Did I round up? I did. It says my result should be 0.02885. So I rounded up to 0.029. Unless I typed in a number wrong. It doesn't look like I did, though. Yeah, everything checks out. All right. If you get close enough to that, I have Canvas programmed to accept your answer, though, so. All right, so let's go back over. We'll just fill this in here. Oh, I didn't click on this. Let's go over here again, and I'm going to give you another problem, and I want you to try this now. So, more or less the same type of problem, except we're going to have you solve for something different at the end. So, this is a sample of adrenaline. There's its formula. I'm going to give you the same mass, 0.10 grams. And I want you to tell me how many atoms of hydrogen are present in the sample. So go ahead and try this calculation. First, highlight what the substances are that you're working with. Then follow where you're going to go on the chart, what you're starting with, what you're ending with, and then try and blueprint it out over your calculation like I showed you. I'm going to give you like 5 or 6 minutes to do this. When you get an answer, type it in the chat. Remember, if you're solving for the number of atoms of hydrogen, you should get a humongous number, right? It should not be something like 0.8 or 7 or even like 55,000. Like, that's way too small, right? It should be times 10 to the something. So there's your hint. I'll check back with you in just a bit. We'll go over the answer then. Let's do 1 or 2 more minutes, then we'll go over the answer, and then it'll be time for a break. So finish up the problem you're working on, and let me know if you have an answer in the chat. All right, let's go over the answer here. So let's go back to this screen. So I'll start up here real quick. We'll just scroll that off the screen there. So I am given a sample of adrenaline, and I'm asked about part of it. So let's highlight. It's the wrong color. There we go. So I've got a sample of adrenaline, and I want to know how many atoms of hydrogen are in there. So those are two different substances. All right, so now what we're going to do is, let's write down what we're starting with here. So I'm just going to abbreviate it ADR for adrenaline. But we're given the mass of adrenaline, which is C9H13NO3. And we'll pull up the chart here. And I can see that I have... Oh, I'm going to sneeze. Hold on. I didn't sneeze, but it's my... You know how you have that sensation in the back of your nose? You're just like, oh, I'm going to sneeze, and then no. All right, so the problem asked me for the number of particles of hydrogen in there. So I'm going to do something like this for my solution. So I'm going to start here. And I'm going to end here. And I guess what I could do is I could just do this. There you go. That's what we're going to do. So let's write all that out. So the first step would be to turn the mass of adrenaline into moles of adrenaline. So let's do that. We'll cancel these units. Now I need to know how many grams of adrenaline there are per mole. So let's go to the Lentech website and we'll type in the formula. So C9H13NO3. And I got 183.20 grams of adrenaline per mole. And then I'm going to turn moles of adrenaline into moles of the component part that we're looking for, which was hydrogen. So let's do that. So we'll put the units down here to cancel. And then we'll look at the molecule. In 1 mole of adrenaline, how many moles of hydrogen are there? Well, there's my number right there. 13. And then finally, we'll say particles of hydrogen, which is what we're looking for. So we'll put this unit down there to cancel it. And then we'll turn this into atoms because that best describes hydrogen. Hydrogen by itself is not a molecule or a formula or whatever. And then how many atoms are in a mole? Well, Avogadro's number of things in a mole. And there you go. We can type all of that into the calculator now, which is what I'm going to do. Divided by 183.20. All right. And I got 4.3 times 10 to the 21 atoms of hydrogen. All right. So hopefully that's what you got. If so, great job. And when we come back from the break here, we're going to do more of these problems. So I have some sample problems here that are going to involve table sugar that I'm going to have you do. But first, we're going to take our break here, because it is that time. And let me get the music going. If I could find the page I'm on here. Yeah, there we go. I should probably unmute the music before I do that too. So, all right, I'll see you in a bit.
憧れのビューティフォースタイル回るディスコボールやってきましたディスコホール目指せ輝くナンバーワン望みは高く限りなくオラのダンステップにみんなハンズアップフロアのテンションはもうライザークラッペハンダベヨースタンダッパ集まってそう固まってヒアウィーゴーだエブリバディレーザービームでレッツラゴー上り詰めるべディスコプリンス宇宙に届けこのディスコダンスみんな大好き I love you ディスコデックそうファンキーナイMIC でチェコワンズオラの話も一遍聞いてくれ熱い魂語るライムスターそうやってきましたアイマスター夢は輝くナンバーワンきっと届くべなてめねこの思いラップデックにみんなハンズアップフロアのテンションはもうライザークラッペハンダベヨースタンダップ滑舌は確実そう確実ヒアウィーゴーだエブリバディチェケラッチョーでレッツラゴー上の方目指す方集めて固めてそして語るみんな大好き I love youしてそう集めれば星になるいつか To the sky 誰だって飛べるのさ夜空を走る王様レモン色に見え I change my life 夏の虹めがけて To the sky 必ず見つけるよ憧れのビューティフォースタイル 友達で紹介すっからな魂回すよ DJ やつのプレイはそう GJ ナンバーワンやつのスピンアップにみんなハンズアップフロアのテンションはもうライズアップクラッペハンダベよスタンダップまとまってそうくっついてキュッキュッキューのパッパッパテカテカテカテカテカみんな大好き I love you ディスコテック so funky nightしてそう集めれば星になるいつか To the sky 誰だって飛べるのさ夜空を走る王様レインボー金色に見え相手にまら夏の虹めがけて To the sky 必ず見つけるよ憧れの Beautiful star
There we go. Sorry about that. Let me pan this out. The music from Katamari is so catchy. So I hope you enjoyed that. Alright, on the screen here, I have table sugar. I'm going to give you about half a gram of it, 0.522. Spoonful of sugar and all that, right? So what I want you to do is answer these 4 questions. Let me put the homework practice on the screen here, too, for you. So in the first one, I want you to tell me how many particles of table sugar are in that sample, how many moles of oxygen are in the sample, how many grams of carbon are in the sample, and how many particles of H are in the sample. So 4 different problems here. If you need the chart, you can always just go back and pause the video on this screen, or you could just pause it right here. I'm going to leave it up on the screen for like 10 seconds. Actually, let me just do this so that it's not on your screen. So you can write down the problems on the next slide and then go back to this chart and just pause or something or whatever you need to do. So here are the problems again. So I'm going to let you do that. And I'll check back in with you in like 5 or 6 minutes. Probably not enough time to do all these problems, but that's okay. Try and do at least 2 of them. And then I'll go over all the answers after that. All right, 1 or 2 more minutes, and we'll go over the answers here. All right, let's go over some of the answers here. I didn't clear this, so I'll need to delete it. All right. Oh, that's not particularly helpful, is it? There we go. Okay. So for all of these problems, we're going to be working with the same sample of sugar. And let me just write down. Oops, I've already messed up. C12H22O11. And so for this first one, I want to turn this into particles of sugar. So that means that I need to go from mass of sugar to moles of sugar to particles of sugar. So let's do that. So we'll cancel out our units. And then in a mole of sugar, how many grams are there? Definitely got to go to Lentech for this one because I can't do this in my head. H22O11, which is 342.30. This is either lactose or sucrose or something like that. And then I want to turn moles of sugar into molecules of sugar. And in a mole, there are Avogadro's number of molecules of sugar. So how many molecules are in this sample? Let's find out. I got 9.18 times 10 to the 20. There you go. All right. How many moles of oxygen are present in this? Now, believe it or not, we can reuse a bunch of these steps. So what I'm going to do from here is I'm going to start copying and pasting some of this. So we've got 0.522 grams of sugar. And we're going to turn this into moles of sugar. And then for this problem, we're going to turn that into moles of oxygen. And that's how we solve the problem. That's all we need to do, right? So for all your calculations here, you're going to have this first part every time, right? Because we're always turning grams of sugar into moles. And then for this part, we're going to turn moles of sugar into moles of oxygen. How many oxygens are in a mole of sugar? Well, there's 11 of them because the formula tells us that, right? It's right here. That's not my calculator, that's my phone. Times 11, 342.30. And what I got was 0.0168 moles of oxygen. All right, we're going to copy and paste this part. So copy, and we'll paste. That looks kind of hideous, doesn't it? There we go. All right. So for the next one, we want to get to grams of C. So we got to go moles of sugar, moles of C, grams of C. And so we can do that. How many moles of carbon are in a mole of sugar? Well, according to the formula, there are 12. And then we'll turn moles of carbon into grams of carbon. And in a mole of carbon, there are also about 12.011 grams of carbon. Oops, that's way too close. There we go. And so when I do that, I got 0.220 grams of carbon. And then finally, for the last one down here, we'll just move this over. Let me put this on the screen just in case you need it still. I'm trying to do this quickly because you guys can pause, but I only have so much time. For the last one, we'll turn moles of sugar into moles of hydrogen, and then we'll turn that into atoms of hydrogen. So I'm just going to write out the blueprint real quick. And then how many H's are in a mole of sugar? Or how many moles of H's are there? According to the formula, there's 22. And then over here, per mole of hydrogen, how many atoms are there? In 1 mole, there are Avogadro's number. And I got 2.02 times 10 to the 22. All right, hopefully those are the answers that you got. If so, good job. All right. That's really this is the most difficult math that I personally think that we do in this class. So if you can make it here, you can make it anywhere in Chem 121. All right. Let's go and do something a little bit easier for the rest of the class, right? Yeah, let's do something nice. All right. What we're going to do in this section is we're actually going to write out actual chemistry. Hooray, finally, right? It's only week 6. So what we're going to do is we're going to take sentences and represent them as chemical equations that you've probably already seen in various sources before. So like I've shown them to you like way earlier in the class when we talked about physical versus chemical properties and changes. You've probably seen them in the labs. Do you have to worry about you always have to worry about sig figs. So my answer had 3 sig figs because the numbers that I was starting with also had 3 sig figs. So if I go over here, so I started with a 3 sig fig number, so my answer should have 3. And again, that 22 and that all the ones are all exact numbers. All right, so our first foray into chemical reactions is going to be simply to just kind of identify what the parts of a chemical reaction are. Later on, we're going to start describing different types of reactions and try and categorize them. And then finally, we'll predict products at the very end of the class. Being like week 10 is what I mean. So, for instance, you may have seen like a statement that said something like this, and you would read that and go, okay, sure. Whatever. Yeah, I drop sodium in water and then boom. But what we can actually do here is we can take this sentence and represent it as an equation like this. And so that's what we're going to do. We're going to start writing out equations that represent these types of observations, for instance. Hey, I mixed these 2 things and I got these 2 things out. Okay, cool. Write it as an equation. So now we can use it for math and stuff. So that's going to be the focus of the rest of the day here, is we're going to look at these equations and try and do stuff with them. I don't know why it's not advancing. There we go. So the first thing that we want to talk about is what does the arrow mean and what are the sides of this equation? So what this arrow is doing is it's trying to give you a before-after state. So when the arrow points from left to right, in other words, it's pointing at the right side as you see it now, the tail end of the arrow is the before state, and the head of the arrow is the after state. You can also think of this as an input-output situation. The things that you input into the reaction vessel are what we call reactants. These are the things that will react with each other. And the reactants typically are going to go on the left side of the equation. They will always go on the tail end of the arrow, though. So if you drew your arrow in some other direction, so like top to bottom or something like that, stick the reactants by the tail of the arrow. Typically, we only really write our reactions left to right. However, there will be an important circumstance where we have a reverse arrow. And so it's important to know what the reactants are in the context of a problem as shown. On the right side are products. These are your output. When you do the reaction, what does the reaction produce for you? It produces the products, and they go at the head of the arrow. Typically, that's going to be the right side of the equation. But again, if we have an arrow pointed in a different orientation, then your mileage may vary. All right, so reactants on the left, products on the right. For now, remember their orientation with regards to the arrow. Reactants at the tail of the arrow, products at the head of the arrow. We point towards the products. The P's go together. Whatever it takes to remember, right? after each product or reactant written in the equation, we're going to have this little parentheses thing that's going to have some combination of letters in it. And what these combinations of letters are for is to indicate what the phase of the reaction is. Or the reactant or the product, I should say, not the reaction itself. This is strictly for an observational perspective. However, in higher level chemistry classes, the phase matters because it's going to contain data in it that will allow you to look up or reference something important. For our purposes in this class, this is just to describe what we see so that if I give this equation to somebody else, they'll know what's going on. Oh yeah, I did see the gas come out. That's what the G meant, right? So the phases are the phases that we have worked with so far. S is solid, L is liquid, and G is gas. So we just indicate what's what and put a little parentheses around it. Now you'll notice that there's another phase there, AQ. That's a new one. What AQ is the aqueous phase. The aqueous phase is just your compound was added to water, but it didn't clump up as a solid and it fell to the bottom. Instead, what it did was it dissolved into ions and is floating around as individual pieces. That's typically what AQ is going to mean to us. AQ can just mean that something is dissolved in the water and didn't dissociate. So, like, for example, covalent compounds don't dissociate into ions. So if you put, like, say, carbonated water, that would dissolve into solution, but it wouldn't dissociate into C's and O's. But for our purposes, pretty much all the times that we're going to see AQ, something is ionic, or at least acidic enough to dissociate. Now, how do you know if something is aqueous versus solid? You have to do the experiment. That's not something that I can tell you, because we would sit here all damn day just telling you, like, what just compounds and whether they dissolve or not. There are so many compounds out there. So, what you'll have to do is either look it up or infer from the context of the problem. The last thing on here are these numbers. You'll notice that this, on the right here, this isn't pointing at anything. It's pointing at the blank in front of H2. Anytime you see a blank, that is to represent a number 1. Otherwise, another number needs to be written in front if it's not 1. Very important, it's not a 0, because 0 times anything is 0. Why would you write it, right? So these numbers are used to balance the equation. And the purpose of balancing an equation is so that you have the same amount of matter going into the reaction that you do coming out. If I mix things together and find out that I have created sodium, like I put 2 sodium in, but then I got 3 out, that's not a thing that can be done in chemistry, or ever, really. We cannot transmute elements into other elements. What you put in is what you get out. So we need to use these numbers to balance the equation. For instance, if I count the number of each element on both sides, here is what we will get. So I'm going to write in blue here. So I would have 2 sodium, I would have 4 hydrogen, and then 2 oxygen. So I should have 2 sodium, 4 hydrogen, 2 oxygen on both sides. Here I have 2 sodium. I have 2 plus 2 is 4 hydrogen, and then 2 oxygen. So those are balanced as written. But now what I'm going to do is what would happen if I got rid of these numbers? So I'm going to just go like this. So if I balance this equation without these numbers here, here's how my balance would change. So I'd have 1 sodium, 2 hydrogen, and 1 oxygen on the right, or I'm sorry, on the left here. But on the right, I would have 1 sodium, 1 oxygen, and 3 hydrogen. And you'll notice that these don't balance out. So if I did this reaction as written, where I took one sodium and one water molecule and reacted them together, I would somehow create hydrogen when I made NaOH and H2. And that's not what happens. That's not what we observe. We do not create hydrogen. That would violate the law of conservation of mass. So balancing the equation is important to get an accurate idea of what's actually happening, because our reactions in reality obey balanced chemical equations. They don't just create random shit because we said it does on paper. The reaction is doing the right thing. We just have to model it correctly when we write it down. All right. So what you're going to be doing is looking at a reaction and balancing the components of it. What the reaction itself is doing, however, is it's just sort of mixing things around like a puzzle. The important thing to note here is that all the pieces have to be used up. So that's where the conservation of mass and our requirement to balance stuff comes from. When you do a puzzle, like a jigsaw puzzle or something, if you shake up all the pieces in the box and then you start assembling the puzzle, you don't have to ever use extra pieces. Like, you don't have to go to the puzzle store and say, yeah, I need more sky pieces. I didn't get enough in my puzzle. Like, that's not a thing that you do. Nor do you, like, attach them to the sides or whatever. Likewise, if you are missing pieces, then the puzzle's incomplete, right? That's no good. So in chemistry, you have to use all of the pieces just the same way. And so that's what we're going to be balancing equations for. So it's very important that whenever you are doing a problem, the first thing that you should do is check your equation. Is the equation balanced? I can tell you that in this class, I will not maliciously write an equation that is unbalanced for the purposes of, did you check the equation to see if it was balanced? However, it is very possible that people can make typographical errors or miscalculations or stuff like that, and they wrote the wrong equation and balanced it incorrectly, and then all of their work is wrong. So if you're in like a supervisory position or something, and you look at the equation and you realize this isn't balanced, you've made a typo or something like that, you could save your company a lot of money just by saying, oh, this should be a 2 here instead of this 1. Oh shit, I was going to buy twice as much reagent as we needed. Okay, thanks for fixing that. All right, so I'm going to just skip ahead of some of these slides here. I'm going to go straight to this example. What we're going to do is we're going to balance the equation in such a manner that we have the same number of each element on both sides. Here is how we do that. So first of all, I'm going to put this little blank in front of each substance. We're going to write a number in here. The second thing I'm going to do is I'm going to find the reaction error and I'm going to draw a line through it, straight down. And we're going to take inventory of both sides. So on the left side, I have carbon, hydrogen, and oxygen. So I'm going to write those elements out. And I'm going to do that over here too, because I have the same elements. And now what we're going to do is we're just going to count. How many carbon are on the left? Well, there's 1 right here, and there's no other sources of it, so 1. How many hydrogen? I got H4, and that's it. How many oxygen? I got 2 oxygen, and that's it. All right, now on the right side of the equation, let's look what I got. I got 1 carbon from right here, so that's good. How many hydrogen do I have? Well, I only have the 2 from the water here, so that's already messed up. And then finally, how many oxygen do I have? I have 2 plus this 1, which is 3. So we have some work to do. Let me get a new color out here. We'll do red. So in order to balance the equations, I need to modify these numbers that are underlined right here. They're all 1 currently, and I have very little space to work with, but that's okay. I need to edit the numbers. I need to change the 1s to something else. And when I do that, all of the numbers will change. For instance, if I were to put a 2 here, I now have 2 carbon and 8 hydrogen. Does that help me? Not particularly. So we're not going to do that. There is a logical route through these types of problems, and that is to put numbers in places that help you the most. For example, I don't think I should put anything in front of either of these carbons because those are already balanced. I don't need to do that, right? Why change the number of carbons if it's already fine? So let's go to the next thing. Let's go to hydrogen. I, again, don't want to put a number here because that would change carbon, but it would also make my hydrogen bigger. That's not super helpful. But this side I'm deficient. So if I put a number in front of the hydrogen in water here, such as, say, a 2, now I have, this should go right here. I just don't have space. Now I have 2 times 2, which is 4 hydrogen. And then I have 2 times 1 is 2, plus these 2 that are still over there. 4 oxygen. So by doing this, I balance out the hydrogen count on both sides. Now I can go to the next element. What do I need to do to balance oxygen? Oh, well, if I put a 2 here, then this becomes 4. So you can balance your equations in this sort of iterative way. And you may have to loop through this a few times until it works out. Depending on where you start, you may just have to loop through a few times. There is a logical starting place, but when you're starting out doing these types of balancing problems, starting anywhere is typically okay. When you add numbers, do you multiply or add? You have to sort of do both. So if I have 2H2O, my 2 would multiply by this number to get the 4, right? However, if I'm doing a tally down here, multiplying this 2 by this O would give me 2, but then I also have to add these 2 over there too. So you're going to multiply the coefficient into the formula it's next to, but then you're going to have to add 2 other elements that are the same in that side of the equation. So just be careful. You do have to do both. All right, so this is just me doing that problem. I'm going to give you a second problem, and I want you to try this one on your own. I'll put some blanks in here. And I want you to tell me what the coefficients are from left to right by typing that in the chat. We'll go over the answers together in just a moment. All right, one more minute. We'll go over the answers. All right, let's go over the answers here. So, again, we'll just split this down the middle right here, although it's a little to the right, actually. We got N and O, N and O. We're just going to tally. My goodness, I have cat hair on the monitor. Oh, the joy of cats, you guys. All right, so we're going to count nitrogens. 1, and then I've got 3 oxygen. How many nitrogen on the right? 1. How many oxygen? 2. Now, the only logical place to start is to start here, but even if I put a 2 here, this doesn't seem like it helps us. Because now my nitrogen is no longer balanced, and my oxygen isn't either. But it does help that we only need 1 of each, so if I do this, then it is balanced, and then everything is all set. So hopefully that was where you started and then finished the problem. You could have started over here, but it would have been a little bit more difficult to see that that was the next move, was to go on the right side. All right. I have several more of these for you to try. We're going to run out of time. I'm going to let you work on them, and then I will put all the answers on the screen so that you have them. I do have some hints for balancing equations. Later on, you're going to start seeing things like polyatomic ions. Keep them grouped together. That tends to help. If you have a very complicated molecule, start there, if you have to at all. You leave the simplest molecules for the end if you can, particularly those that just have hydrogen or oxygen. For instance, water is a good one to get towards the end with, and then oxygen is even better than that. The last thing I would advise is if you end up with huge numbers, kind of like an arms race situation, where the products go up and then the reactants go up and the products go up and the reactants go up, and you just go back and forth and back and forth and back and forth. What has happened is you have made a math error. If you miscount something, then you'll never be able to balance it, and you'll be like, what the heck is going on? And your numbers will just get bigger and bigger and bigger and bigger and bigger. If that's the case, erase everything and start over. Because you have missed something, and then fixing it means you're going to have to just reduce all your fractions out anyway. When you do this, you should have the lowest common numbers possible. So if everything is divisible by 4, for example, do that. So I'm going to put these problems on the screen. Actually, we are out of time, so I'm going to just leave these for you to try. So you can pause the video and write these down before we do the little outro here. Because there's not really much point in me saying, okay, go ahead and try these problems for 2 minutes when there's that many more of them to do. So when we come back tomorrow, I will write the answers on the screen for you for these. But I will leave the answers off for now, just so that you don't have to look at them and can't do the problems. All right, I do want to thank everyone for coming out to the lecture. We will finish Chapter 6 on Monday next week. We have just a little bit left, and then we're going to start Chapter 7, which I believe is gas laws and then other fun things. So lab worksheet number 3 will be formally assigned tonight. I will go in and put the assignment up in Canvas after my afternoon class. So that will be due next week at some point. But quiz number 5 is due tonight. It will close tomorrow. Make sure you get that in by the deadline. That's all I got. Hope everybody has a wonderful evening. Get those assignments done when you can, and have a good weekend. Take care.